everyone, welcome to MathCamp. My name is Aramais. I am a PhD student in Agricultural Economics department. The idea of the MathCamp is to teach you how to think mathematically. So it's good if you have some understanding on calculus techniques, but mostly the accent here will be on how to do proofs. Let's start the lecture by understanding what is actually mathematical logic. So first let's define what is statement. Statement is anything we can say, write, or otherwise express which can be either true or false. So it's, in a short way, is a statement is something that is true or false. So for example, x squared is equal 9 is a statement. Fx is equal absolute of value of x is continuous is a statement. So for something to be a statement, it has to be either true or false. But no statement is both true and false. So as long as we understand what is statement, now we need to move further and understand why a statement is valuable for our purposes. So the thing is, we usually use the statement for forming new statements out of old ones. So now we will learn a couple of techniques how to combine statements to have something valuable to making proofs. So I will go over three basically things: conjunction, disjunction, and negation. The other things is in your lecture notes so you can read it. Conjunction is a logical operator, and suppose we have two statements, P and Q. So the conjunction of P and Q, which we note by is the statement that true if both P and Q are true, and false otherwise. So the best way to understand the definition of conjunction is something which called truth table, and you will appreciate this truth table when we will do actual proofs. So suppose we have two statements P and Q. So we said that P and Q is true if both of them true. So the statement P can be true and the statement Q can be true. Then if both are true, we have true. If one of them true and if P is true and Q is false, then P and Q is false. The same way, if we have false and true, we have false. And if we have false and false, we have false. For example, P can be it's raining today, and Q can be it is cold today. So if it's raining today and it's also cold today, then this both P and Q is true. Otherwise, if it's raining today but it's not cold, P and Q is false. So the other logical operator is disjunction. So let's make definition here. So disjunction is, we say P or Q, if P and Q are statements, P or Q is true if either P is true or Q is true, or both, and false otherwise. Let's try to make a truth table for P or Q. So if P true and Q true, P or Q is true. In the case true false, again we have true. For false true, we have true, and when both of them are false, we have false. So a simple example can be, let's say, a statement that in your first semester you will take Econ 629 or you will take Stat 630. So if you take either of these class, then this statement is true. So the last logical operator that I want to speak is negation. So you will see a lot of negations in your Econ 629 class. So we define negation of P to be the statement which is true if P is false, and is false if P is true. So the truth table is looks like following way. So if P is true, then negation P is false, and if it's false, then negation is true. So for example, if the statement is let's say Alice is a PhD student, then negation P is Alice is not a PhD student. Now let's talk a little bit about strategies for proofs. So we will learn three main strategies for proofs and some of their cases. But before jumping into doing that, we need a little bit review of quantifiers or operators. So one of the common used quantifier is universal quantifier, which denoted this way. So if Px is some statement and U is a collection of all values of x, then when we say for all x in U Px, this means that the whole statement is true if for all x in U Px is true. So if there exists at least one x for which Px is not true, then this whole thing is false. So the second common used quantifier is the existential quantifier, which has the following denotation. And when we say there exists x in U such that px, so this statement is true if we can find at least one x in U such that px is true. So as an example, suppose that the possible values of x are all Agicom PhD students, and y is types of classes offered by Texas A&M, and let's txy be the statement that person x takes class y. So if we try to interpret let's say following. So what we are saying that all Agicon students are taking all classes that are offered in Texas A&M, which is basically nonsense. For example, there exists y such that for all x txy. So the statement said that there exists at least one class such that all PhD students are taking this class, and this is true since if a class is econ 629, then we are done. Now let's go into strategies for making proofs. So the first strategy is direct proof. The direct proof has the form as based on some logical operator which called conditional operator. When we have two statements P and Q, then the conditional operator has following truth table. So if P true and Q true, then this is true. If P true and Q false, then this is false. And for the rest, it's true. So basically the conditional from P to Q is true if it's never the case that P is true and Q is false. So the only case we have P conditional from P to Q is false when P is true and Q is false. So direct proof viewed in this form. So direct proof, suppose we have two statements PQ. So we start by assuming that P is true. So the statement P is true, and we produce a series of steps, each one following from the previous one, and which eventually leads to Q. Then we do a chain of sequences that are added to initial statement P such that we reach to the final statement of Q. Let's do example. So suppose n and m are integers. So what we want to prove that if n and m are both even, then m plus m is even. So basically P here is n and m are both even, so this is our P statement, and m plus m is even is our Q statement. So what we want to prove that if n and m are both even, then m plus m is even. So we do it by direct proof. So as we said, direct proof starts by assuming that P is true. So assume n and m are both even. So recall that the number is even if we can write it as a multiple of 2. So it means we can write that n is 2 times k and m is 2 times l. We want to show that m plus m is equal 2 times some number c. Since n and m are even, then we can write that m plus m is equal 2 times k plus 2 times l, which is equal 2 times k plus l. So if we denote this as a c, we'll have this is 2 times c, and we are done. So from here it follows that m plus m is even, and we are done. One more example. So let a, b, c be integers, and we want to show that if a divides b and b divides c, then a divides c. So a divides b means there exists some q integer such that iq is equal b. Proof is by direct proof. So what we are saying, let a divides b and b divides c. So we want to show that a divides c. Okay, so now we are building our chain of consequences. So since a divides b, then we can write, so from here a times q is equal b, and b divides c. So from here we can write that c is equal some l times b. Let's denote this 1 and this 2. So from 1 and 2 follows that c is equal l times a times q, so which is equal l qa. So if we denote l times q by some m, let's say, so this is equal ma. So from here, by definition of what we mean divides, so follows that a divides c, and we are done. You may note already that direct proofs looks like something like this. We write, suppose statement P, then we do some argument which builds our proof, and then we say, so this follows that Q is true. Next technique for proof is by contrapositive and contradiction. So my favorite one is contradiction. So my rule of thumb is, if you are doing some proof, then if you don't know how to prove it, from where to start from contradiction, and usually it works. Let's start from contrapositive. So if we have two statements P and Q, and what we want to prove is following, then so if you go back and look the problem 6 in unit 1, where I proved conditional negation Q to negation P is equivalent to conditional P to Q. So contrapositive, to do contrapositive, we start by saying that Q is false, and then by step-by-step argument we go from negation of Q to negation of P. A proof of this sort is called proof by contradiction. Now let's draw some example of contrapositive. So let n be an integer, and what we want to show that if n square is even, then n is even. So remember, our interest in to proving the following, and the contrapositive says that, and in this case P is n square is even and Q is n is even. So we start by saying that, and we talk that this is equivalent of following, so we will start by negating Q. So proof by contradiction, by contrapositive, is following. We start by saying that, so contradicting Q, it means n is not even, so it's the same as n is odd. And we want to show that P is false. So in other case, what we want to show that n square is odd. So since n is odd, we can write that n is equal 2 times k plus 1, where k is some integer. So from here, n square is equal 2k plus 1 square which is equal 4k squared plus 4k plus 1. So, but we can write this as 2 times 2k squared plus 2k plus 1. So the thing you need to note that this is integer, this square of integer is integer, and if we denote it by some m, we can write the whole thing as 2m plus 1. But this is just definition that the number is odd. So from here follows that n is odd. And we are done. So now let's talk about the proof by contradiction. So if we go back to lecture 0 problem 7, then there I show that not conditional P2Q is equivalent that P and not Q. From here, if we prove that P and not Q is false, so we can conclude that not conditional P to Q is false. Therefore, not conditional P to Q, which is the same as conditional P to Q, is true. This is the idea of proof by contradiction. So what we are doing, we are saying that suppose by contradiction Q is false, and then the goal is to prove that P and not Q, negation of Q, is false, and then we are done. So let's do example of proof by contradiction. What we want to show that the number square root 2 is irrational. So we start by saying that suppose square root 2 is rational. So if it's rational, then we can write square root 2 as ratio of two integers. So this is the definition of the rational number, where m and n are integers with no common factors. If there are some common factors, then we can cancel them. So from here, the statement that m and n are integers, without no common factors, are one of the important parts of the proof. So at the end, we are going to have argument that m and n has common factor. So in that case, we are going to conclude to contradiction. From here, we can write that 2 is equal m squared over n squared. So we have that m squared is equal 2 times n squared. Thus, m squared is even. But we prove that m squared is even, then from here m is even. If you remember the last statement we proved, where we use the proof by contrapositive, we conclude that if m squared is even, then m is even. So if m is even, then from here we conclude that m squared is actually is divisible by 4. So thus, if it's divisible by 4, then n squared is even, since n squared should have some part of 2. So from here n is even. So what we conclude that if both two numbers are even, from here follows that m and n are even, and if two numbers are even, they have common factor. Which is a contradiction of the following statement. So from here we conclude that square root 2 is irrational. So now we are going to learn some of the combinations of the direct proofs and contrapositive and contradiction proofs, where we are doing proof by case, or when we have even only if option. Let's start by the case by case option. To understand this, again, suppose we want to prove following, where P and Q are statement and such that P can be written as the or statement of A and B, A or B. So if we go and read the lecture note 0 problem 3, there I prove that the statement is equivalent to so basically when we do case by case, to prove this thing, we are going to separate problem into two subproblems and prove that both are true. Let's do example of this. So example is, so we suppose let n be an integer and we want to prove that n squared plus n is even. So we do basically direct proof, but separate the problem into two cases. So the first case is n is odd. So when n is odd, we can write this as 2k plus 1, where k is a integer, and n square is 2k plus 1 square, which is equal 4k square plus 4k plus 1. And n square plus n is equal 4k square plus 4k plus 1 plus 2k plus 1, which is equal to 4k plus. So what you can see that separately each problem is, each component is even, and we know that sum of the even numbers is even, so the whole thing is even. Now let's do, so this was the case 1. Now let's do case 2. So the case 2 is, as you may already guess, n is even. So what we proved previously, if n is even, then n square is even. So as a reminder, so it's when n is even, we can write n as a 2 times k. From here, n square is equal 4k square, which is even. So from here, sum of the even numbers is even, then we are done. And we prove that each case is true. It follows that the whole thing is true. So this is a basic example of case-by-case proof. Now let's have the option if and only if. Again, we will use the results obtained from lecture 0. So if and only if option. So if you go back and look on lecture 0 problem 4, we show that to prove that this thing is true, we need to show that this is true and this is true. So basically we are going into two directions. And now let's do example. So suppose m and n are integers. What we want to prove that if we want to prove that m times n is odd if and only if m and n are odd. So we do this direction. So here we say let m times n be odd, and we want to show that m and n are odd. So let's do by proof by contradiction. So proof by contradiction, we start negating that m and n are odd. So suppose not. So what basically means that this means at least one of m or n is even. Without loss of generality, m is even. So from here we can write that m is equal 2 times k. So m multiplying by n is the same as writing 2k times n. But this is integer, and we can write this as a 2 times some l, where l is k by n is integer. But from here follows that m times n is even, which contradicts this part. So from here follows that m and n both are odd. Now let's do the other direction. So the other direction is m and n are odd, and we want to show that m times n is odd. So let's do it by direct proof. We say let are odd. So we can write from here m is equal to k plus 1 and n is equal to l plus 1. From here m multiplied by n is 2k plus 1 multiplying to l plus 1, which is, if we multiply, we get 4kl plus 2k plus 2l plus 1. So the thing you can note this, these three components are even, and when we add 1 to even number, we get odd. So from here we can conclude that m times n is odd. And this is end of the proof. Finally, the last strategy we are going to learn is proof by induction. So the proof by induction is a very useful method when we want to prove certain type of statement that involve natural numbers. So to be more precisely, induction is a method that can be used to prove statement of the form, let's say, for all n in n Pn, where Pn is a statement that involves n. So the usual way to construct proof by induction is following. So this is actually theorem which proof can be found in any real analysis book or even in Unit 1 of MathCom lecture notes from Dr. Wallace. So, theorem is following. Let Pn be a statement which involves n, and this holds for all n in n. Then, if we provide a proof that P1 is true, and provide the proof if Pn is true, then Pn plus 1 is true, then what we have is that Pn is true for all n in n. So let's do a couple of more examples. The first example, suppose n is in n, that what we want to prove is that 1 plus 2 plus n is equal n times n plus 1 over 2. So here is step 1. So we follow the basic proofs of strategy for proving by induction. So by induction, so we say that now we want to prove that this holds when n is equal 1. So 1 is equal 1 times 1 plus 1 over half. So this is true. So next step 2 is, so we suppose that 1 plus 2 plus n is equal then we want to show that plus n plus 1 is equal times n plus half over 2. Now, we know that 1 plus 2 plus n plus 1 is equal, since this is this by assumption, then we have this. From here we have that this is equal, if we take n plus 1 out, then we have n half plus 1, which is equal plus n plus 2 half. So we prove step 2. And what step 3 said, that since step 1 and step 2 are true, then by induction denote this by 1. 1 is true. Now let's do one more example. Actually, this is our last example for today's lecture. So we want to prove that 1 cube plus 2 cube plus n cube is equal n squared times n plus 1 square over 4. So we prove by induction. So what we say step 1 n is 1. So we have that 1 cube is equal 1 square 1 plus 1 square over 4, which is true. Step 2. We prove that this holds for n. We say, suppose it holds for n. And we want to show that this is true for n plus 1. So we want to show that this is true. In the proof by induction, we know that this is equal to this. So we do very basic thing. So we take n plus 1 square out. So the thing you can notice that this expression is just n plus 2 square. So we end up proving that the whole summation of cubes is equal this, which we want to prove. Okay, that's all for this lecture.